Hi there, everyone. My name is Justin Shade. I'm a tech with the Paveda Lab as part of this REU program. And today we're going to be discussing the preference and performance of the Seedcorn maggot under different environmental conditions. Okay, so to begin, we have to talk about the reproductive cycle of the Seedcorn maggot. So the Seedcorn maggot is a generalist fly species, and it feeds on decaying plant and animal matter. It lays about 270 eggs over the course of its life, and it has a lifespan of just over 24 to 25 days. And so the way they reproduce is they oviposit around seeds in disturbed soil, which is usually freshly tilled, freshly planted soil. And the larvae eventually hatch out of the eggs and use the nearby seeds as a food source. And so for that reason, it's a potential agricultural pest. As they feed on seeds, it causes damage to the crops that they would grow into. So to move on, we have to talk about this diagram here, which is a visual representation of what the life cycle might look like. So at the beginning of spring, early spring, you have the adult seedcorn maggots, which lay their eggs in disturbed soil. The eggs eventually hatch into larvae, and the larvae burrow into nearby seeds. From then on, they continue to consume the seed, reach a sufficient mass, and they pupate. And then eventually those pupa emerge as adults from the soil, and that happens 3 to 5 times within a growing season. So that happens 3 to 5 times, and then temperatures get colder, you get towards the fall, and the final generation of larvae pupate, and they overwinter. They stay in their pupal form through the winter to insulate themselves from the cold, and then emerge again the following planting season. Okay, so let's talk about some of the consequences of seedcorn maggot development. So as I mentioned earlier, the seedcorn maggot larvae, they burrow into seeds and they eat the embryos and the seedlings as well. So that includes roots, shoots, cotyledons, and other parts of the seedling. And what that causes is a phenomenon known as stand loss. Now, in stand loss, the embryo of the seed is consumed, and so the plant never grows. And that's not easily noticeable without a reference point. So it may take several weeks to say, hey, we planted 100 seeds and only 50 of them ended up sprouting. That's particularly problematic in New York because we have a short growing season. Winter comes on hard and fast. And because of that, if farmers see that 1 month in, only half the corn they planted grows, they don't have time to go and plant another generation. It will never reach maturity by the time winter rolls around. Another problem is slower germination rates, which don't affect the final yield in theory. But again, in New York, it's also a problem. And it is impacted because, again, winter comes on too fast to have things germinate slowly. Okay, so let's talk about seedcorn maggot prevention. What has historically been done to prevent seedcorn maggot infestations? Well, usually farmers have used neonicotinoid treated seeds. Now, neonicotinoids, they're a broad spectrum insecticide, and they kill seedcorn maggots in the larval stage. So they eat the seeds treated with the pesticide, and some of those are pictured above. They're color-coded to show that they've been treated with pesticide. And they eat it, and it's toxic to them, and they die. However, this also has effects on non-target species. Bees are one particular example. The neonicotinoids are absorbed through the seed into the plant, and then it eventually ends up collecting in other parts of the plant, such as the nectar, and bees are one of the affected species. When they drink that nectar, they are affected. It also contaminates groundwater as rainwater washes the neonicotinoids off the seed into the water table. And for that reason, they are banned in Europe, and New York State is also considering a potential ban. Now, that ban has actually been putting pressure on farmers to find alternatives to neonicotinoids. Which brings us to a research question. How do environmental conditions, both managed and unmanaged, affect seedcorn maggot oviposition preference, survival rate, and larval performance? So we researched 3 different factors. We looked at nutrient availability, planting depth, and soil moisture. So with respect to nutrient availability, farmers can apply different types of soil amendments, which are basically, I put fertilizer in parentheses, but it's different ways of adding nutrients to the soil. So did they use organic fertilizer? Did they use inorganic fertilizer? Did they use compost? And all of that impacts nutrient availability. Next, we look at planting depth. Farmers can choose to plant their seeds at different depths, and that could potentially limit the access of seedcorn maggot larvae and adults. And finally, we looked at soil moisture. So we know that precipitation patterns change throughout the year, and irrigation is another factor. And those both impact how moist the soil is. That can impact their performance. So first, we looked at nutrient availability, and we hypothesized that seed corn maggot mothers would seek out the most nutrient-rich environments, and they would have a greater rate of survival and performance in those environments. So this is the kind of trend that we were expecting. So we expected corn, and then corn with meat meal to have a higher preference. For context, meat meal is essentially dehydrated meat powder. And it's another way of adding additional nutrients to the soil. Beans are more nutrient dense than corn, so we expected that to even have a higher preference. And then our highest we expected was the beans with meat meal, because that would have the most nutrients. Okay, so these were our methods. We had these oviposition cups set up. The filter paper was on top to collect the eggs. And then you had the soil in the cup below that. And below that, you had a additional cup for the purpose of irrigation. The cotton wick brought the water from that cup up into the top cup. It's kind of like hydroponics in a way. And that kept the soil moist. So we had 5 different treatments, one with nothing in it, that's our control, one with corns, beans, corn with meat meal, and beans with meat meal. We had 10 cages and 20 flies of an equal sex ratio in each. Okay. So we found that beans with meat meal did have the highest preference, which is what we predicted in terms of the eggs laid. The survival rate was also highest in beans with meat meal. And in terms of average weight, there was no significant difference except in the control, which makes sense because there's no seeds, therefore no food source, and the corn. So like I mentioned earlier, there was strongest preference in the beans with meat meal sample. There was no difference in performance or weight, and some of that error that you saw was, some of the error bars are pretty large. We attribute that to a large number of variability. There was a lot of zeros in there. We had samples where nothing survived. And that's just part of working with seed corn maggots. All right, so next we checked out planting depth. And we predicted that seed corn maggot mothers would seek out the deepest seeds to oviposit in. And we saw that because we had read literature that said that shallower planting depths were associated with less seed corn maggot damage. So therefore, deeper planting depths must result in more damage. And so we also hypothesized that at those deeper depths, they would have a greater rate of survival and performance. So this is the kind of trend we expected. We planted seeds at 1.25 inches deep, 1.5 inches deep, 2.5 inches deep, and 3 inches deep. And we expected the performance to go up as we got deeper. This is our setup. We had our control with nothing in it, 1.25, 1.5, 2.5, and 3. Sorry, said those in reverse order. But 10 cages, again, same setup with the flies of equal sex ratio. Okay. So in terms of our position preference, there was no significant difference. In terms of our average weight, there was no significant difference except in the control, which again has no food in it. And the survival rate was, again, obviously very low in the control. But 1.25 and 1.5 were the highest, while it decreased significantly at 3 inches depth. So there's no oviposition preference, as I mentioned earlier. No significant difference in the average weight, and the survival rate was highest from 1.25 to 1.5 inches. Coincidentally, that's also the optimal depth for lima beans to germinate. The lowest survival rate, as I mentioned earlier, was at 3 inches, but we also noticed that lima beans did not germinate at all at 3 inches. None of them did, so we predict that it could have possibly been because they were denied a food source, that survivability was lower. Okay, so next we look at soil moisture. So we thought that seed corn maggot mothers would seek out moist but not flooded environments to oviposit in. And again, they would perform the best in those moist but not flooded environments. So expect it was a kind of curve like this where we added 10, 20, 30, and 40 milliliters of water to different samples. And we expected survivability to be higher from 20 to 30, but not 10, which would be too dry, and 40, which would be too moist. So our control was hydrated by Wicks. That's our saturated soil. Then we added 10, 20, 30, and 40 milliliters respectively. And our cage setup was the same as before. And this is what we found. So with respect to our egg count, they actually preferred the 10 milliliters the most, which we didn't expect. With respect to our average weight, it decreased significantly. Our survival rate, rather, it decreased significantly at 20 milliliters, but was highest in the saturated soil. And our average weight was the same across the samples. So as I mentioned, there's a strong position preference of 10 milliliters. The survival rate was highest in the saturated soil. And you might not have noticed it on the past slide, but there was complete mortality past 20 milliliters. Nothing survived in the 30 or 40 milliliter sample. And just for reference to put that in a way that's easily comprehensible, in the 30 and 40 milliliter samples, it was like an inch to an inch and a half of water on the top of the cup. So anything in there was probably going to drown. So let's move into our key takeaways. Seed corn maggots, we found that they prefer a higher nitrogen content. And there's potential for that in trapping. It may be setting bait with a high nitrogen content. Irrigation, we found that could be a potential deterrent of oviposition because of the flooded cups and the seed corn maggots not preferring to oviposit there. And soil depth was also a potential tool, but it would require deeper germinating seeds. You know, what we're really in is a catch-22 because the same thing that hurts the seed corn maggots can also help the seed corn maggots, and it could also just kill the plants outright. For example, you know, you can flood a field, but that's going to kill your crops. And if you flood a field and it dries out a bit and it's moist, seed corn maggots like that. You can plant the seeds deeper, but your plants might not germinate at all if you plant them deeper. So for those reasons, we definitely have to test these factors under field conditions before we make any prescriptive recommendations to farmers. And those are our next steps for this study. All right, thank you. Questions? I'll be taking questions now. Sure, Dahlia.
Thank you. Thanks. That was wonderful.
Thank you.
I'm curious regarding your rain experiment with the water.
Mhm.
How much does the 10 milliliter compare to like rainfall in like New York? I didn't see like a depth for like the actual soil. So I'm curious like what the actual real world comparison for the amount of water added is to real world rain conditions.
Oh, you know, that's again why we would have to test these in field conditions. You know, lab conditions are very different. We could add 10 milliliters, but there's, I wouldn't say there's a good analogy to approximate what that would look like in the field based off of this. Because again, you know, there's rainfall per square inch and just a lot of calculations involved in what that would look like in terms of a big field.
Awesome. And then my second question to that is regarding the meat meal your lab used.
Yeah.
Do you think if you guys had tried a different nutrient additive that perhaps there was some sort of chemical the maggots were attracted to in the meat meal that they may not be attracted to for other types of fertilizers?
So in our lab, we actually have people working on, we have Lily working on VOCs in some bean crops. Hello.
Awesome. Thank you.
But yeah. Anyone else have questions? Cole?
I would just like to say you had a great talk.
Thank you. Really appreciate it.
What would you say was your biggest challenge that you faced throughout the summer?
Oh, our biggest challenge. So we had to run a few trials before we could even run these to make sure that this setup would actually work. The whole filter paper on top of the cups, we hadn't tried that before. And we just had the idea, hey, what if we put some filter paper on top of here? And we had to try different orientations of the filter paper to see what would catch the eggs best and what would keep the filter paper moist, because the filter paper needs to be kept moist for the eggs to survive and the flies to oviposit there. So getting that down probably took like 3 mini experiments and mini trials.
Okay, I think we're out
Alright.
of time. So thank you.
Thanks. Appreciate it.